So in this video I will be solving part 2 here, where we will be assuming that the decrease in air temperature with altitude can be modeled entirely by the adiabatic reversible expansion of pockets of air of ideal gas, starting from the basic equation of fluid statics, and we will derive expressions for the air pressure and the air temperature as a function of altitude. So again, as the problem states, we will be dealing with adiabatic reversible expansion of pockets of air. And it's important to keep in mind that these pockets of air are an ideal gas. And then adiabatic reversible basically means, adiabatic means that all the thermal energy is conserved. There's no loss of heat throughout the problem. And then reversible means that the pressure in the pockets of air is equal to the pressure outside of the pockets of air. So it said that we will be starting with the basic equation of fluid statics here, which is the change in pressure over the change in altitude is equal to the negative of the pressure times the molecular weight over the gas constant R times temperature as a function of altitude z times the gravitational acceleration. So how we're going to start this problem is we're going to be using internal energy. So the internal energy du is going to be equal to the change in heat dq minus the work P times the specific volume dV. So now, since we know that this is an ideal gas, we can simplify this du into the specific heat capacity at a constant volume times the change in temperature, since this is an ideal gas and reversible. And then our dq is just 0 because it is an adiabatic situation. So then we can substitute in for this P as well, which will just be PV equals M RT. So it'll just be RT over V dV. And then now, since we have a separable differential equation, I'm going to get them on all the T's and V's on the same side. So first thing I'm going to do is divide this T over to this side and divide CV over to here. So we'll get integral of dt over t is equal to negative R over CV, and then the integral on this side dV over V. So now we need to define the bounds of these integrals. So how we're going to do that is we're going to consider a certain altitude. We're just going to say like sea level 0. And we will know the temperature, pressure, and volume at that, which the temperature will be 273 kelvins, the pressure will be 1 atmosphere. So we're going to be calling that T1 as our start, and V1 and then it will just be going to our variable T and our variable V. So now we can evaluate these integrals. Obviously it'll be the natural log. So this one will be natural log of T over T1. And then this constant will stay the same. And this one will be ln of V over V1. And then now what we're going to want to do is get rid of these natural logs. How we can do that is we're going to add these constants into our natural logs, and then multiply or raise everything to e to get rid of the natural logs. So first we're going to put this negative in here, and then we'll just flip this. So it will be V1 over V. And then we're going to multiply this over to the other side and put it in this one. So we'll get C over T1. And when you add something into a natural log, it'll just raise everything inside there to that power. So it'll be the inverse of this. So the C V over R. And now we can use the ideal gas law, since we want everything in terms of temperature and pressure. That's what the problem asks. So we can use the ideal gas law to substitute in for these V's. So PV equals RT, so V equals RT over P. And the R's will cancel. RT over P, so we will have T1 over P1 over T over P, which would also be T1 over T times P over P1. So now we can multiply this over to the other side, and that will just add 1 to this exponent. Since we're just adding another T over T1, so it'll be T over T1 to the C V over R plus 1 is equal to P over P1. So now what we can do is we can simplify this exponent by just adding R over R as this one, so we get CV plus R over R in this exponent. So I'm going to rewrite this up at the top. as T over T1 T over T1 CV plus R over R, and the right side will stay the same. And now we can use an equation for enthalpy, which will be equal to, again, our internal energy plus the work, PV, but we can substitute this PV for RT because it's an ideal gas. PV equals RT. So RT. And then we're going to want to take this to the derivative of T. And since this is an ideal gas, we know that the enthalpy will equal the specific heat capacity at a constant pressure times, again, the derivative of temperature. And then the internal energy, again, will be the specific heat capacity at a constant volume times the derivative of temperature dt, and then plus our R dt. And as you can notice, these dt's will all cancel, and we will be left with Cp equals Cv plus R. So we can substitute that in up here, and we will get that T over T1 to the Cp over R equals P over P1. And then now we want to solve this for T. So I'm actually going to write this up here under this equation. Will end up being T for some pressure is going to be equal to, if we flip this exponent over to the other side and then multiply by T1, so it'll be T1 times P over P1 to the R over Cp. So now we are going to be able to substitute this in to our basic equation of fluid statics here. So to substitute this in, the left-hand side will stay the same, obviously. And now we will have negative P M G over R, and this is where our T1 will be substituted in, and it will stay on the bottom. because it is on the top here, so it'll stay on the bottom. And then for these, I'm just going to leave these p's out here. So for p, it will be to the negative r over cp. And then P1 will just be to the R over CP. And that will be because our P1 here is in the denominator of the denominator. So that means that the exponent will be positive. And then here, this P is in the numerator of the denominator. So that means that exponent will be negative. And now what we can do is we can combine these p's. So that will just make this p to the 1 minus r over cp. So, yeah. And now what we're going to want to do is get our p's on the same side and integrate like we did before, since this is a separable differential equation. So firstly, I'm going to get this p over to the other side, so it'll end up being p to the r cp minus 1 this time, dp, because it'll be that 1 will turn negative and that rcp will become positive since we are dividing. And then our constants, and we'll be taking the integral of this, so I'll leave that there. And then we're going to leave our constants out front, so it'll be negative P1 to the R CP G over R T1, and then our integral and dz. So now we just need bounds for this integral, and we're going to do it just like before. P1 to P, Z1 to Z. And now to evaluate this, I'm going to put in our dummy variables here. We will have P to the R over CP multiplied by CP over R. And that will be evaluated from P1 to P. And then our constants will stay the same. And then this integral will just be z minus z1 . And now we can notice that these r's here will cancel. and we can divide this CP over to the other side and evaluate this. So it'll end up being P to the R over CP minus P1 to the R over CP will be equal to negative P1 to the R over CP multiplied by Mg over T1 times CP, and our Z minus Z1 will still be here as well. So now what we can do is add this over to the other side and factor out our P1. So it'll end up being that P to the R over CP is equal to P1 to the R over CP 1 minus this whole thing here. And now we can raise everything to the CP over R, and we will get our equation for pressure as a function of altitude. So again, we're raising everything to the power of CP over R, and that's what we'll be canceling out these exponents and then raising this to that power. So we end up getting that our pressure as a function of altitude is P1 times 1 minus mg over T1 times CP, and parentheses Z minus Z1. All raised to the CP over R. And now, all I have to do to get our temperature is plug this in up here. So what we can do is divide our P1 on both sides of this equation, and we will get P over P1. So then we can just substitute this part into here, and now we'll cancel out this exponent, R over CP and CP over R. So through that, it'll end up being that T is equal to just what's in these big parentheses here times T1. Mg over T1 CP. To make this a little bit more clear, there we go. Z minus Z1. So this will be our final equation for the temperature as a function of altitude, and this will be our final equation for the pressure as a function of altitude.